Scientists are warning of an impending strong earthquake near the San Andreas Fault, potentially occurring as soon as this year. Recently, San Francisco experienced a series of earthquakes near the San Francisco Zoo, emphasizing the seismic activity in the area. The first, a magnitude 3.5 earthquake, occurred on January 10, 2025, at 11:02 p.m. local time at a depth of 7.9 kilometers, with an epicenter approximately 5 kilometers northwest of the zoo. Tremors were felt across the northern peninsula, with varying intensity based on local geology. Shortly after, at 11:36 p.m., a second earthquake of magnitude 2.2 struck the same area at a depth of 8.0 kilometers. While smaller and less noticeable, it signified ongoing activity. Hours later, at 2:48 a.m. on January 11th, a magnitude 2.9 earthquake occurred at a depth of 8.1 kilometers, slightly north of the earlier events. These earthquakes unfolded within a compact area, raising questions about their connection and potential implications. Although these events are minor compared to the catastrophic potential of the San Andreas Fault, they serve as a reminder of the region's dynamic geological processes. Residents reported varying experiences of the tremors, with those on firmer ground describing sharp jolts, while those in softer soils felt prolonged shaking. Understanding the recurrence intervals of earthquakes and fault behavior is vital for those inhabiting or studying the Bay Area. The San Andreas Fault, known for its ability to release vast amounts of energy, has historically shaped the region's geography and urban resilience. This situation underscores the importance of preparedness in a region where the Earth's movements are an intrinsic part of life. The fault's size and length significantly influence the magnitude of earthquakes it can produce. Experts estimate the San Andreas Fault could generate an earthquake up to magnitude 8, though not beyond, as larger magnitudes like 8.5 or 9 are usually linked to subduction zones. The recent magnitude 3.5 quake, while modest, was felt widely in San Francisco. The city's unique geology, characterized by bedrock and areas of unconsolidated fill, amplifies the complexity of tremor experiences. Coastal regions built on unconsolidated marine sediments often experience more pronounced shaking due to seismic energy amplification. Despite its small size, the earthquake's location on the San Andreas Fault allowed its effects to spread further than similar quakes on smaller faults, with tremors reported as far as the Santa Cruz Mountains and Sacramento Delta. The geological setting plays a critical role in how earthquakes impact the Bay Area. Areas built on solid bedrock, such as serpentine rock, experience shorter and less intense shaking, providing natural stability for construction. In contrast, zones underpinned by loosely compacted sediments amplify seismic waves, leading to prolonged and more severe shaking. Shear wave velocity measurements versus 30 provide insights into these variations. Higher versus 30 values, indicative of compact formations, correlate with greater stability, while lower values in coastal areas highlight susceptibility to intense shaking. For instance, while bedrock zones exhibit velocities of 760 meters per second or more, coastal regions with loosely compacted sediments may show values as low as 178 meters per second, classified as Site Class E and highly susceptible to severe shaking. Historical seismic activity provides additional context. A review of earthquakes with magnitudes of 3.5 or greater since 2000 reveals a consistent pattern of minor tremors across the Bay Area, though none of substantial magnitude. Both the San Andreas and nearby Hayward faults remain highly stressed, raising concerns about the potential for significant events. These faults traverse densely populated areas, making seismic preparedness crucial. Despite the relatively low frequency of magnitude 3.5 or greater earthquakes directly on the San Andreas Fault in recent decades, the 2025 event is the largest on this segment in over 20 years, serving as a stark reminder of the fault's potential. The Greater Bay Area exhibits a clear pattern of seismic activity influenced by its geological diversity. For example, Oakland and much of the East Bay generally have lower shear wave velocities, with firmer ground mainly found in the hills or coastal ranges. In contrast, areas like the Santa Cruz Mountains, where the San Andreas Fault runs directly, tend to exhibit higher shear wave velocities, resulting in sharper and more abrupt jolts during earthquakes. Meanwhile, San Jose features significantly lower average shear wave velocities in its upper subsurface layers, characterized by soft soils. These conditions suggest a greater likelihood of prolonged and severe shaking during major seismic events. The recent magnitude 3.5 earthquake has raised questions about whether it is an isolated event or a precursor to something larger. The San Andreas Fault, stretching from Central California through the Bay Area into Northern California, has a storied history of earthquake recurrence intervals, indicating the potential for significant future activity. This fault, known for its vast energy release, continues to shape the region's landscape and necessitates preparedness due to the varying geological conditions. On December 5, 2024, a magnitude 7.0 earthquake occurred in the region, marking one of the most significant seismic events in recent history. While such powerful quakes are infrequent due to the fault's recurrence intervals, they highlight the ongoing seismic risks posed by the San Andreas Fault. Historically, the San Andreas Fault has exhibited recurrence intervals of 200 to 300 years in its northern segments, such as near San Francisco, and about 110 years in its southern areas like Santa Cruz. The infamous 1906 earthquake is a stark reminder of the fault's catastrophic potential. Other faults in the region, such as the Hayward and Napa Creek faults, also pose significant risks. For instance, the Napa Creek Fault produced a magnitude 6.0 earthquake in 2014, while the Hayward Fault, with a recurrence interval of approximately 170 years, is nearing its average threshold for a significant event. These intervals represent averages, and the actual timing of earthquakes can deviate significantly, with periods of quiet or clusters of activity shaping the seismic landscape. San Francisco, situated toward the northern end of the San Andreas Fault, is now approaching the later stages of its estimated recurrence range. The recent magnitude 3.5 earthquake has a statistical likelihood of 5 to 10% of being a foreshock, potentially preceding a larger event. Should this occur, it could escalate to a magnitude 4.5 or even 5, which, while relatively modest, could still be noticeable. More destructive events, such as the 2014 Napa earthquake, magnitude 6.0, underscore the importance of monitoring activity along critical faults in the Bay Area, including the Calaveras and Hayward faults. Frequent smaller tremors, particularly in regions like the geysers, add to the dynamic tectonic activity of the area. Beyond the Bay Area, seismic activity in regions like Seattle also highlights significant risks. On January 20th, 2025, a series of events struck the Seattle fault zone, including a magnitude 3.5 earthquake, suggesting a minor swarm of seismic activity. The Seattle fault zone, which lies directly beneath downtown Seattle, poses a significant threat due to its potential to produce a magnitude 7.5 earthquake. Historical records reveal that the last major earthquake on the fault occurred approximately 1,100 years ago, with evidence of 3 to 4 significant events over the past 3,000 years. This suggests an average recurrence interval of roughly 1,000 years, and with 1,100 years having passed since the last major rupture, the area may be approaching another significant seismic event. Recent seismic data, including smaller tremors like a magnitude 3.9 earthquake in 2023, serve as reminders of the fault's potential. The Seattle fault's proximity to urban areas amplifies its risk, similar to the Newport-Inglewood Fault in Los Angeles. Geological studies have identified ancient slips along the Seattle Fault, providing a clearer picture of its activity and recurrence intervals. While estimates vary from 200 to 15,000 years, the evidence of recurring significant events within the past 3 millennia suggests that vigilance and preparedness remain critical for both the Seattle area and the broader tectonic regions it influences. Seismic activity observed over the past few years reveals a concerning pattern of smaller earthquakes, concentrated both to the east and west of fault lines. These events, often aligning in linear patterns, suggest a connection to fault systems. For instance, earthquakes recorded between 2020 and 2024, with magnitudes ranging from 2.6 to 3.9, hint at an underlying buildup of strain. While no large earthquakes have occurred recently, these trends emphasize the need for continued vigilance. Ignoring the gradual rise in activity could leave regions unprepared for the next major event. The Seattle Fault, in particular, poses a significant hazard due to its proximity to densely populated areas. Unlike faults located offshore, such as the Cascadia subduction zone, a rupture along the Seattle Fault would deliver direct and potentially catastrophic impacts to Seattle and its surrounding areas. The uncertainty surrounding the fault's recurrence interval adds to the urgency for preparedness, as geological records suggest that significant strain may be nearing a critical threshold. Reviewing the fault's activity reveals that it is overdue for a major earthquake. Historical evidence shows that the Seattle Fault has been active 3 to 4 times over the past 3,000 years. This places the current period dangerously close to another large event. The recent uptick in seismic activity, including a magnitude 3.5 earthquake felt across parts of Seattle, Redmond, and Tacoma, serves as a reminder that the fault remains very much alive. While a 3.5 magnitude earthquake is not particularly powerful, it contributes to the growing body of evidence suggesting the fault is not dormant. Similar activity in recent years reinforces the idea that the region remains at significant risk. This situation is not unique to Seattle, as seismic activity appears to be increasing globally, particularly in regions such as the Nankai Trough, Taiwan, and Japan. Notably, a magnitude 6.0 earthquake struck Taiwan today, followed by additional smaller quakes. Further seismic activity was recorded near the Japan Trench and the northern Mariana Islands, suggesting a broader pattern of pressure transfer within the Earth's crust. The Nankai Trough, a critical seismic zone where tectonic plates converge, is experiencing heightened activity. This region is closely monitored as substantial strain continues to build. The last major earthquake there occurred in 1944 with a partial rupture of multiple fault segments, while a full rupture in 1857 caused a massive megaquake. Given the current seismic activity, the Nankai Trough is considered a prime zone for future earthquakes. The southern end of the Nankai Trough, in particular, has experienced substantial swarming, including a 6.8 magnitude tremor earlier this year. These movements suggest that strain is building across the entire fault system, not just isolated ruptures. If this pressure continues to increase, the region could experience a major earthquake, potentially in the magnitude 8 range, accompanied by a devastating tsunami. This underscores the critical importance of monitoring the Nankai Trough and its surrounding seismic zones, as the likelihood of a significant earthquake in the near future appears to be rising. As we've seen, seismic systems worldwide, including the San Andreas Fault in the San Francisco Bay Area, remain active and unpredictable. Recent tremors in these regions serve as stark reminders of the potential for much larger seismic events. While smaller earthquakes provide valuable insights into the region's tectonic activity, they also highlight the ongoing buildup of pressure along major fault lines. It's not a question of if the next big earthquake will strike, but when. Staying informed, prepared, and vigilant is essential as we continue to monitor these evolving seismic conditions.